Meet the main character of our story. His initials are HVK. His name is Hilge. He is a young kid, only about 18 years old. He is currently a senior at his high school in Sweden. He lives in a two-dimensional world, a flatland. Everything he does and knows about is restrained to the two dimensions he's known his whole life. This is the school Hilge goes to. He's a very smart child and has taken all of the hard math classes in his school, except for one. He is currently taking the hardest math class in his school, two-dimensional geometry. This class deals with the hardest math topics, cyclic quadrilaterals, Cevians, and even 9-point circles. Because he is so smart, the class is easy for him. He often resorts to dueling in class, which is a very bad habit, but it satisfies his longing for knowledge. One day he draws the Fibonacci spiral, a spiral based on the recursive Fibonacci sequence. Another day, he starts drawing a sort of fractal. He draws an equilateral triangle, then draws 3 more equilateral triangles with 1/3 side length on each side of the initial triangle, and so on. This fractal, eventually known as the Koch snowflake, is named after the smart Hilge. However, one day he has a weird thought. What if there's more to this world than 2 dimensions? With this mysterious thought, he draws a new doodle. He calls this masterpiece the 3-dimensional square. However, we know it better as a cube. Although this seems simple to us, this doodle was revolutionary in Hilge's time period. Here we can see a rotating animation of a cube. Again, although this seems naive to us, Hilge found it fascinating that a 3-dimensional cube could be rotated on a 2-dimensional plane. In fact, we can take this even farther than 3 dimensions. Here's something truly fascinating, a 4-dimensional cube being rotated on a 2-dimensional plane. This 4-dimensional cube is called a tesseract. This is very hard for us to intuitively visualize and grasp because we are so comfortable with and used to only 3 dimensions in real life. Let's take it one level farther. Here's a 5-dimensional cube, or pentaract, being rotated. This seems, and is, even more complex. Because we are used to 3 dimensions, this animation probably doesn't make much sense to us. In order to better understand n-dimensional cubes, it might help if we started the basics. A dot. Although this is really a circle, let's pretend it's a dot. A dot is 0-dimensional. It is a component of any n-dimensional cube. Here we have a line. Notice that if we take the dot and drag it a certain length, we form a line. A line is 1-dimensional. Now we repeat the same process. We drag the line down perpendicularly into the 2nd dimension, thus forming a square. A square is 2-dimensional. Once again, we drag the square into the orthogonal 3rd dimension and form a cube. This cube has 8 squares or 2-dimensional faces, 12 lines or 1-dimensional faces, and 8 points or 0-dimensional faces. Although this is hard for us to visualize, dragging the cube into the 4th dimension forms the 4-dimensional tesseract. Here is a sort of map of a tesseract. We see all the coordinates of each vertex of the tesseract. Each set of 4 numbers is a vertex of the tesseract. Each connecting line represents an edge, and each closed loop of points represents a face. For example, from 0, 0, 0, 0 to 1, 0, 0, 0 to 1, 0, 0, 1 to 0, 0, 0, 1 back to 0, 0, 0, 0 is a closed loop and is one face of the tesseract. Here's a similar map for a 5-dimensional cube, or pentaract. Notice how it is much more complex. It has many more points, vertices, edges, faces, and cubes or cells. How can we tell how many 2-dimensional faces or 5-dimensional faces an n-dimensional cube has? Well, for the number of k-dimensional faces of an n-dimensional cube, the formula is n choose k times 2 to the n minus k. There are n choose n minus k or n choose k ways to fix a vertex, and for each vertex, there are 2 options, 0 or 1. This is the intuition behind the formula. Here is a chart with various values for k-dimensional faces of n-dimensional cubes. Notice how the numbers increase. All these values agree with the formula in the previous slide. That's all I have to share with you about n-dimensional cubes. I hope you gained something from this. Remember, although reality restricts us to 3 dimensions, math can always take us farther.